difference between this is just that there's a sulfur on here. Right? And this is the redox reaction here. So here, a hydride ion is transferred to NAD+. If we have time later, I'll show you the mechanism with respect to lactate dehydrogenase, which we'll study at the end of today or next time, by which the hydride is transferred to NAD. So you have that in your notes. But here, NAD is being converted to NADH by virtue of a transfer here, and the formation then of a covalent enzyme intermediate. So this is also an example of covalent catalysis. Right, so we've got redox going on here. Okay, this is getting reduced. This is getting oxidized. Right, C double bond O is formed, right, and linked to S. So this is oxidized as compared to that. And NAD is reduced. Okay, so it takes us to here. We've already done the redox part of the reaction. We've got a covalent intermediate. And now let's look at what happens next. So what happens next is first NADH dissociates, that's a physical step. Then NAD rebinds, but now it's rebinding as a substrate for the next round. This is not another redox step. Right? This is not NADH leaving an NAD plus adding on as if it were another redox step, because that would undo what we just did here. Right? So this is just the enzyme getting set up for another round. Then the other substrate binds. That's finally we get to the inorganic phosphate binding. So you see why it's ping pong, because we've lost the product, we've lost NADH before another substrate binds. Right? So then here, the phosphate attacks to resolve the enzyme, reform the thiolate, and form the product. Okay. So this is the redox reaction. This is an exchange step, just physical release and rebinding. Right? The implication here is since the enzyme starts out eating NAD+, forms NADH, this NADH is going to go off to the electron transport chain. We're going to have to regenerate NAD. And in the normal course of events in the oxygen-breathing cell, NADH will transfer its electrons on, and in that process, it reforms NAD, right? Because that's the other side of the redox couple for NADH and NAD back again. So that's how it gets regenerated. Okay? Now, if you have no oxygen to deliver the electrons to, you have to do something else. And so that's where the fermentation comes in that we'll get to at the end of the class. Okay? So this is an interesting enzyme. It's the first redox enzyme, and it's a ping pong example, and it generates a very high energy compound that we can then use to make our first ATP. Yeah?
Does the NAD plus that comes back in, does that play any kind of regulatory effect on the rest of the mechanism?
I don't think so. I don't think so. This is not a regulatory enzyme. So it's not regulated as part of the cellular metabolism. It's possible, I'm not sure if this is shown this way because there's an obligate order of binding. It might be that you need the NAD to bind here before phosphate binds. So in that sense, it would be, might cause some conformational change. Yeah. Okay, so the next step is the substrate level phosphorylation to make ATP. Okay, so here we've got 1,3-BPG, which we just formed. We've got ADP, right, ADP. So the hydrolysis of this compound, if you were to add water across this bond, is substantially more negative in terms of its free energy of hydrolysis as compared to the plus 30.5 you need to get from here to here. And so the overall delta G0 prime is minus 18. So we've coupled ATP synthesis on an enzyme with the thermodynamically highly favored breakage of an acyl phosphate linkage. Notice that this enzyme is called a kinase enzyme. So usually these enzymes are named with respect to the substrate. So if you're going to talk about a kinase, then this is what's being kinased or phosphorylated, as if the reaction were going that way. Right? So sometimes these enzyme names don't make too much sense. You could look at this reaction and think about it going this way and say, oh, that's a phosphorylase, because it's taking a phosphate off, right? Unless you want to think of it as a kinase that's adding it to ATP, to ADP. So you can see it's a little bit ambiguous. So, you know, obviously the important thing is to remember that whether it's a kinase or a phosphatase just depends on how you're looking at it. And just the standard name is to call it a kinase. Okay? So this is a straightforward nucleophilic attack on an electrophilic center to generate two products. No covalent intermediate. Okay, next we have a pretty cool enzyme, it's a mutase. So now we've got an example of a rearrangement reaction, so a different category of our enzyme type. And this is, the enzyme is called phosphoglycerate mutase. And before phosphoglycerate mutase can function in glycolysis, it has to get phosphorylated. It has to be covalently modified on a histidine here, so that the histidine is actually, one nitrogen on the histidine is actually linked to a phosphoryl group. So some other enzyme comes along and does that. And then the enzyme functions catalytically in that modified state. I think this is the first example we have of that. So, there's no such thing as a phosphorylated histidine in the genetic code, and yet if we don't have that, the enzyme is not able to work as a catalyst. So the mutase reaction is simply a rearrangement. This phosphate is moving from C3 to C2. And it's probably pretty intuitive to suggest that this compound and this compound are roughly similar free energies. So this delta G0 prime is near 0, plus 4 is pretty much near 0. So one of these two, there's two histidines in the active site. So one of them is phosphorylated by some other enzyme that comes along, and the other one is not phosphorylated. Okay? And so the way that the mechanism works is that the C2 carbon, which is not phosphorylated in the substrate, right, attacks the phosphorus, the oxygen here on the C2 carbon, attacks the phosphorus on the phosphorylated histidine, right, while the other histidines serve as a general base to take the proton away to facilitate that reaction. So this nitrogen, unphosphorylated, grabs a proton. This guy takes the phosphoryl group off of this histidine, and we're forming then right, a dephosphorylated histidine here, and a compound that now has two phosphates on it. Right? But the reaction is to move the phosphate, not to leave you with a complement that has two phosphates on it. Plus, if you left two phosphates on it, at the end, the poor enzyme would have to get phosphorylated again, right? And that would cost more energy. So the original enzyme here that's got the phosphate on the histidine, that costs ATP. Right? The enzyme that actually put that thing there had spent ATP. Right? So we want to be able to, we want to have the enzyme recapture that. So the same histidine that gave up, that was the product of the nucleophilic attack in the first step, then attacks the phosphate, this time at the other position. Right? So you might imagine, well, there could be some small change in rearrangement of the active site to facilitate that histidine being in the right position with respect to C3 instead of C2 now. Right? So the other histidine now functions as a general acid to get the proton away. And now you're back to the resting state, and this sugar has moved has been transformed from 3PG to 2PG. So no net change in oxidation state, no net use of any high energy cofactor, simply the employing of an enzyme that was invested with a phosphate group on a key histidine residue in the active site that also has another histidine in the active site. And so together those two histidines are helping this phosphate move from one position to another on the sugar. Yeah?
So since we have such similar delta Gs for this, and would we think that this would not be a good regulatory step? This
Yes,
is
that's
go-
correct. This is not a good regulatory